Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us today. Today is part 3 of our 4-part series on the IEC 61131 programming languages. Specifically today, we are covering function block diagram. Now, the IEC 61131 programming languages are very popular worldwide, and there's a lot of customers from Horner using them, specifically in Europe and Asia, and a growing list of customers here in the US. But I guess because of the sheer size of the installed base of our advanced ladder customers, we probably don't give IEC 61131 the time we should on this channel. But in this series, we're rectifying that, and we're providing you with the information you need to decide if maybe IEC 61131 is right for your projects. Okay, here's how we're going to break down the topic today. Just as in the previous 2 episodes, we're going to start with a short review of IEC 61131 and how to enable it in Cscape. Then we're going to focus on function block diagram as a language, its strengths and its weaknesses, and we're going to spend plenty of time demonstrating how to use it in Cscape. Now, IEC 61131 is the IEC standard for the implementation of PLCs. It consists of 5 languages: ladder, which we covered in episode 1, structured text last week, function block diagram is this week, and next week we'll talk about sequential function chart. We're not going to talk about instruction list. It's more of an assembly type language that isn't used all that much anymore. Now at Horner, we talk about standard IEC and enhanced IEC. Keep in mind that everything we're covering in this series can be handled by standard IEC. But there is an enhanced version available that if you use, you can get more variable support, faster execution, and the ability to perform online programming and simulation. However, it does require a small one-time license fee per controller, and it's not supported in either the micro OCS or the XLE and XLT. Now, to enable IEC 61131 programming in Cscape, you will have to go to the Tools Application Settings area in Cscape and make sure you check the Support IEC Editor Programs option. After doing that, every time you start a new project, you will be given the option to program that project in IEC 61131. Now let's talk about function block diagram. Function block diagram is a graphical programming language that in a lot of ways is similar to ladder diagram. Function block diagram uses a lot of the same function blocks as ladder, which is one of the big similarities, but instead of mimicking an electrical line drawing like ladder does, function block diagram has the look and feel of an electrical schematic. Now, the advantage of that electrical schematic type view is it helps make FBD intuitive and easy to follow. It also makes debugging very easy, as you can easily follow the signal path. It's also great for process control, as you can trace your analog inputs through a series of function blocks as you process the signal all the way through to the end. FBD does have some weaknesses. It's not nearly as familiar to programmers as either ladder logic or as structured text, so it does take some extra training. Also, FBD takes up a lot of space and can sometimes become unwieldy for complex diagrams. That also can make it time-consuming to edit, as sometimes even with a small change, you have to do some rearranging to keep things nice and readable. Let's get started with demonstrating how to use function block diagram in Cscape. As part of our demonstration today, I'm going to show you 3 different ways in which you might use function block diagram in your project. We're going to start with some discrete logic, move on to some analog signal processing, and then I'm going to show you a PID implementation. Here we go. Let's get started with function block diagram. I'm in Cscape. Let's go ahead and do File, New, and we can choose IEC 61131. Okay. And let's go ahead and set up our environment. So we've got our navigator over here to the left. I would definitely also want to have our program variables available as well. Our toolbox is over here on the right. Everything looks good. So let's start in the control section of our program. Expand one more time, and under main loop modules, let's right click and select new logic block. And we want function block diagram for this demo. So this is our layout here. It's shown in a grid, and we have a series of basically buttons that we can press here for editing, adding a function block, adding a variable, adding a comment, and a whole variety of them as we move up and down the list here. The ones you're going to use most often are going to be at the top of the list. And this little dotted box here is for selecting or editing or moving things around. So let's start with a demo where we're going to do some discrete logic. So again, we'll go back to the old start-stop circuit. Now in a traditional start-stop circuit, you basically have all your start push buttons in parallel with a seal from the motor starter, for instance. And all those in parallel, all those contacts in parallel are effectively OR statements. And then in series with that, you have all the things that can stop the motor. You know, your stop push buttons, your e-stop enable, all those sorts of things. So we're going to have an OR function block in series with an AND function block, and then the output of that is going to be our motor starter. Okay, so here we go. So let's start by putting a function block on the screen here. So by default, it just picks one, and it's happened to pick multiply, which is the default one. We can double click on this, and we can select the function block that we want, and they're all categorized. So for Boolean logic, we select Booleans, and for all of our push buttons and our seal, we want the OR function block. The things that are going to be in parallel or going to be OR'd are going to be the start push button and the seal for the motor starter, the seal contact. So let's select OR, and 2 input pins is all we need for this OR block. So now we've put our OR block down. The next thing we have to do with function block diagram is we need to put down variables. So I'm going to go ahead and click here and put a variable down. We're going to have 2 variables total. I'll put another one down, and then we'll go with that as a start. And then I'll go back to my element selection box here. So the first thing we're going to have in as the OR, the first element in the OR, is going to be our start push button. Okay, so let me go ahead and type that in. I'm just typing this in on the fly. And it's Boolean and global, and we'll go ahead and map that over to a real world input number 1. And then in parallel is going to be the seal contact for our motor starter. So I'll type that in here. Again, I'm creating these variables on the fly, and this time we're going to map that, let's say, to output Q1, because that's a real world output. Now with function block diagram, what we do is we connect. I'm going to go ahead and rearrange these here. We basically can connect the output of our variables to the input of our function blocks. And you can see what I did there was I placed my mouse over the output section of the variable, and then I clicked and dragged and established a connection there. Now generally, if your connection is legal, in other words, you're using the right type of variable that matches what the input of this function block is requiring. See, when I hover over the function block, it shows me that both inputs as well as the outputs are Boolean. As long as everything matches, this line will remain gray. If I pick the wrong type of a variable by accident, what you'll see is you'll actually see this be colored like red, for instance. So after our ORs, we're going to have an AND block, because the output of this needs to be ANDed with our stop push buttons as well as, let's say, our e-stop enable. So I'm going to grab another function block here, and I'm going to place it on the screen. And I'm going to go ahead to make things look neat. I'm going to go ahead and kind of line things up here. Oops, I think I'm going to line them up. Well, maybe not. What I have to do is I have to select my selection option before I can move things around. In this case, again, I don't want to multiply. That's the default. What I want is I want an AND block here. And again, that's under Boolean, and I want an AND block. And this time I'm going to want 3 input pins because I need the output from my OR, I need my stop push button, and I need my e-stop. So that's 3 pins, not just 2. So I'm going to increase this number to 3 and hit OK here. And then I'm going to start out by connecting the output of my OR to the input of my AND. And then I'm going to drop a couple more variables here for the AND block. The first one I'm going to drop is going to be my stop push button, which we will go ahead and memory map to %I2 because it's a real world switch. And let's go ahead and connect those two there. I'm going to slide this back a little bit to give me a little more room for my next variable, which I will put here. And this one is going to be my e-stop enable. Okay. All right. And this one will make input number 5. Okay, we'll say that's where that one's wired. Okay. And then we need to connect that up to here. All right, and I'm going to move this just to make it a little more readable. There we go, so those lines aren't running into each other. Now I do have one problem here, and that is my stop push button is a normally closed type scenario. So it's when my stop push button is not pressed that I want this AND condition to be true. So therefore, I need this to be a negated output. So how can I do that? Well, what I can do is I can click on the connecting line and I can press the space bar, and then a little circle appears here that basically shows that this is a negated signal. So what I'm ANDing together is the OR of my start push button and my motor starter seal contact, the NOT of the stop push button, and the e-stop, which has to be on. It's typically normally open. And then the output, once again, is going to be my motor starter. And I could just drop another variable, or I can just highlight and copy, Control C, and paste, Control V, my motor starter contact. And then make sure I click my selection tool and then connect up the output of the last function block here with the motor starter. So this ought to be the logic I need for a simple motor starter. Another thing it's always good to do is to comment your work. So I'm going to go ahead and add not a variable, but a label to my logic here. I'll double click on it and I'll say something like start, stop, example. And then I can resize that or whatever I want to do. And then if I want to move things around editing wise, I can highlight these and then kind of move them around as, you know, one group. And I think I'm good to go. Let's double check and make sure I haven't made any mistakes. I'm going to go ahead and do an error check. Okay, there's only non-fatal errors. Why are there non-fatal errors? I haven't put anything on the screen. So that's why there are some non-fatal errors. But there's no fatal errors. That's good news. My screen is empty, screen 1, but that's not a big deal. Do I want to continue? I'll say yes. And then let's go ahead and download this program. Actually, let's not do that yet. Let me go ahead into my hardware configuration, and I'm going to need to go in here and make sure I set the IP address appropriately so that, because I'm programming over Ethernet, so I don't lose my connection halfway through. Let's also go to my local I/O, and I'm going to go into the analog inputs, and I'm going to change these to 0 to 20 milliamps. Okay, and I'm going to set my filtering up a bit and say okay. Okay, so now that I've done my hardware configuration, I'm going to go ahead and download this program. Again, it's telling me that I didn't put anything on the first screen, but that's okay. And then it's warning me that, hey, your hardware configuration is changing, but that's also okay because I made sure my Ethernet address and my I/O configuration was set the way I wanted it. So once this is done downloading, we can just go ahead and go into debug mode and see what it looks like. So I think we're done with our download. Let's go ahead and select debug, and let's see what things look like in debug mode. Okay, so the things that are not basically on, or the things that are not on, are in blue. The things that are on are in red. So you can see neither our motor starter nor our start push button are on. Our e-stop switch does happen to be on. It's controlled with switch 5, so I can switch it on and off here. I'll go ahead and leave it on because in a normal condition we want our e-stop signal to be on. Okay, my stop push button is off, which is what I want. So to start the motor starter, all I should have to do is to turn on the start push button and off again, and then you can see the motor starter is on and it's being sealed in, which is good. And then I can go ahead and flip the stop push button switch 2 to turn everything off again. Okay, so that first demonstration was a success. That's showing you using logical operations in function block diagram. In our next demonstration, we're going to show you how to do a little bit of analog signal processing in the function block diagram language. Okay, back to Cscape. So let's add a little bit more logic here. All right, I'm going to start out with a comment, just so we know what we're dealing with. And this will be, let's say, pressure sensor signal processing is the comment we're going to use here. Go ahead and shrink that up a little bit. There we go. So what do we want to do here? Well, let's say that we have a pressure sensor connected to analog input number 1, and we want to go ahead and scale that to PSI as a real value. The first thing we're going to have to do, because all of our analog inputs always come in as integers, we're going to need to convert that integer value into a real value. So let's drop our variable here, and we'll select our, oops, there we go. We'll select our pressure sensor that's straight from our analog input. So we've dropped our variable there. Now we want to convert that variable over from an integer to a real. So let's add a function block. And then let's double click on it to select the right function block. We can go to conversions, and then we want an any to real conversion. And we don't have our choice of number of pins here. This is just a fixed amount. So another handy thing you can do here with function block diagram to make things more readable is you notice how we kind of lost some of the description of this function block. I can actually stretch the size of that guy out so we can read the whole thing. That's really nice. And then let me move it up a little bit here. And let's go ahead and connect our pressure sensor to the input of this function block. Remember, if we hover over this, we should be able to see, there it was, I just missed it, I wasn't patient enough. If we hover over that, we should be able to see what our inputs are. Our input is really any numeric format. Our output needs to be a real. So after we convert from an integer to a real, the next thing we want to do is a scale block. Now, of course, I can add another function block like I've been doing the entire time, or I can go over here to my toolbox and drag and drop one on here as well. So under, I believe, advanced, there should be a real scaling block available to me. So I'm going to click and drag it over. And now I have a scale real, and it's big enough to show everything. I'm just going to stretch it out a little bit more. There we go. And then the output of my integer to real conversion I'm going to go ahead and connect to my scale reel here. And then I've got 4 other inputs that I need to connect here. So let's go ahead. I'm just going to make these constants. They could absolutely be variables, or some of them could be variables and some of them could be constants. I'm just going to make all of these constants. And I can go ahead and I can drag these. I'll just put 4 of them on 4 of them here. And let's start with the first one. Let's close out on this one here. Let's start with the first one, and that's our minimum input. Let's say we know our inputs are scaled from 0 to 32,000. That's what the raw counts are coming in as. And then let's say that our pressure sensor output is 10 to 100 pounds per square inch. Let's say that's the scaling on this particular sensor. All right, let's scoot these over a bit. All right, to give us a little more room. And then let's connect the outputs here. And if we want to, after we've done our connections, we can kind of move things around a bit. I tend to like to have these things so that they're not overlapped. There we go. All right, so that is the scaling there. And then, of course, the output of this scale block is going to be what we're looking for, and that's the pressure in pounds per square inch as a real value. So let's drop another variable, say here. Double-click on that guy, and I believe I've already created that variable. Yep, pressure PSI, which is a real value, and I'll connect the output of my function block to that variable. Okay, so that should be the logic we need for this simple signal processing we're doing on our analog input. Now, I also, in between demos, I also did some work on my screen. So I've got a screen here where I'm showing the pressure in raw counts as well as the pressure after we've scaled it. So I should be able to go to the bench and see that in real time. Let's go ahead and download that. I'm pretty confident I got all the syntax right. So I'll skip the actual error check. And sure enough, everything was fine. And we'll go ahead and download that. And then once we're done downloading, we'll take a look at debug to see what that looks like. And then we'll take a look at the unit on the bench and see what that looks like as we modify our input. So it looks like our download is just about complete. Let's go ahead and switch into debug mode. And let's see what debug looks like for numeric values. Okay, gives you some nice detail. As you can see here under the pressure sensor, it's giving us the integer value on the analog input. It's also giving us the scaled value on the output side. So lots of nice detail here under debug. And then let's go ahead and take a look at what it looks like on the bench. This first switch here, I believe, is my analog input. And you can see as I increment my analog input, you can see my scaled value is shown as well. Okay, so that's a little bit of relatively simple analog signal processing. Hopefully that gives you an idea of some of the things you can use function block diagram for when it comes to analog signals. For our last demonstration, I'm going to show you an implementation of PID in function block diagram. So let's head to Cscape. Now, before I show you specifically the PID implementation, I want to refer back to the help file here, because the help file is a great resource, especially when you're exploring new languages and new function blocks and those sorts of things. So if you go to the contents of the help file, you'll notice that there's a section called Creating and Editing Control Logic, and you can expand this, and then you'll see you've got an IEC User's Guide here. Down here we've got languages. We've got the 5 different languages called out here. I can go ahead and select function block diagram, and it gives me some details on that. And then there's just a wealth of information here in the help file. So I would definitely encourage you to reference the help file as you're developing your programs. back to Cscape. Okay, so instead of drawing it from scratch, what I thought I would do this time is just show you one that's already implemented. So from a PID standpoint, again, function block diagram is very similar to ladder in a lot of ways. So with the IEC package, you do have some additional options when it comes to PID. So you have both integer-based PID, which is what we use in advanced ladder, and it's highly effective. And then there's also a floating point version as well. But let's focus on the integer version here. And if we go down to our toolbox and we take a look at PID and scroll a little bit, we can see we have our choice between independent and ISA. And then we also have the choice between with or without auto tuning with each of these choices. So, and then we've also got some manual mode function blocks here as well. So what I've drawn here on the screen is I've got my PID loop here. It's the ISA version without auto tuning. All right, and you can see, just like with advanced ladder, we have to assign, the first input here is an array of 16 consecutive integers, which contains a variety of important information for the PID loop. And then in addition to that, you've got your set point, your process variable, and then your manual enable and your manual up and down. Now again, if we hover over this function block, it's going to give us the details on specifically what we need from an input-output standpoint for this function block. If I can get it to hover properly. Oh, I almost had it there. There we go. So you can see that the first input is an integer array. Set point and process variable are integers, and then the last three are Boolean on the input side, and our output control variable is also an integer. But one of the nice things in function block diagram, it's an extra function block that we don't necessarily offer in advanced ladder, is we have this setup function block here. Very useful. So this really details a variety of parameters that you might need to set up for PID. So it needs to reference the same 16 integer array for both the PID loop and the setup block. And then you can have either constants. Again, these first several are integer values, and the last four setup parameters are Boolean. And in this case, I just wanted those to be 0 because I just wanted the defaults for all of these. So I set the always off contact for each of these last four parameters. And this is just a real clear way to set up your PID so you can see what's happening. You can see all the values. These are just constants I have here. Everything that's a variable is clearly called out. So this is just really nice. And again, if we go into debug mode, all right, we're going to get a pretty nice display here where we can see what's currently on, off, etc. And then for all of our variables, we're able to see the set points as well, or we're able to see their current values on everything, again, that is a variable. Very handy. And then if we go take a quick look at my overhead view here, you can see I've added a control valve to my demonstration. So as I change my pressure reading, you can see my control valve adjusting as well. Okay, so again, we mentioned in our slideshow that we thought that process type applications and process type logic is a pretty good fit for function block diagram. And we think it's a real clear way to call out that sort of logic and those sorts of function blocks like PID, for instance. So hopefully that is something that you can use in future projects if you decide that the IEC 61131 languages are right for you. Okay, let's go ahead and wrap up our session for today. Function block diagram is a popular IEC 61131 language that bears some similarity to ladder, but it looks more like an electrical schematic which makes it easy to follow. Now, in most applications, FBD is one of several languages that's used in the application. It's not often that it's the only language used for the entire application. Now, I want to remind you, we're here every Tuesday at 2 o'clock, either fully live or streaming live a pre-recorded video. And we're always available to answer your questions live Tuesday at 2 o'clock. Now, if you choose to watch our programs on replay, we're still looking forward to your comments and questions in the comment section, and we respond to those just as fast as we can. Now, next week is part 4, the final installment on our series on IEC 61131, and we're going to cover sequential function chart. That's kind of the language that can tie everything all together. Okay, now I'm looking forward to presenting that material to you next week. That's all we have for this week, but before I go, I want to remind you, if you haven't done so already, don't hesitate to subscribe to our channel. Of course, it doesn't cost anything, and if you choose notifications as you subscribe, you'll be notified every time we go live or every time we post a video. Okay, until we meet again, let's all get out there and do us some good this week.